Science advances not by locking in early impressions, but by revisiting them as data improves. Many of the largest named structures have been refined, redefined, or reinterpreted as surveys expanded. Some grew larger, others became less distinct. A few quietly faded into the background as broader context emerged. There is also a temporal element. These structures are observed as they were in the past. Light from distant regions has travelled for billions of years to reach Earth. What is seen is a snapshot from long ago. The universe has continued to evolve since then. Connections may have strengthened or weakened. Matter may have shifted along filaments. The present-day configuration is inferred rather than directly observed. All of this makes definitive statements difficult, and that is not a weakness. It reflects the scale of the problem. The largest structures push observation, theory, and imagination to their limits. They sit at the edge of what can be measured reliably. Caution becomes a virtue. Gentle humour can be found in how eagerly humans seek superlatives, the biggest, the longest, the most extreme. The universe responds by offering candidates, each with an asterisk attached, perhaps this one, depending on how measured, for now. Rather than providing a final answer, these name structures serve another role. They highlight how scale transitions from objects to patterns. They show that bigness, at the largest levels, is not about singular dominance, but about arrangement. About how matter traces the invisible scaffolding of gravity across immense distances. They also remind observers that knowledge grows unevenly. Some regions of the universe are understood in exquisite detail, others remain sketchy. What feels like a firm conclusion today may soften tomorrow as new data fills in the gaps. In this way, the largest named structures function as milestones rather than destinations. They mark how far observation has reached, not how far reality extends. They sit comfortably within uncertainty, inviting continued exploration rather than closure. By resisting definitive answers, they perform an unexpected service. They keep the question open, not as a problem to be solved once and for all, but as an ongoing conversation between data, theory, and perspective. And in that openness, the idea of the biggest thing begins to feel less like a prize to be claimed, and more like a lens through which the universe slowly reveals its complexity. As the scale widens further, something subtle but important begins to change. Structures that once felt tangible start to lose their edges. What could be pointed to, named, and outlined now becomes harder to isolate. Size no longer belongs to objects alone. It starts to belong to patterns. At these extreme scales, astronomers often speak in terms of statistical clustering. This does not mean guessing or hand-waving. It means recognizing that matter in the universe does not arrange itself into neatly separated units once distances grow large enough. Instead, it forms tendencies. Regions where galaxies are more likely to be found. Regions where they are rare. The structure exists, but it exists as probability rather than as a solid shape. This shift can feel uncomfortable at first. Humans prefer clear borders. A mountain has a base. A river has banks. A city has limits, even if they are debated. In the universe, once structures span hundreds of millions of light years, those instincts stop working. Density changes gradually. Connections thin out rather than ending. What counts as part of something depends on how closely it is examined. Consider a cloud drifting across the sky. From a distance, it looks like a single thing. It has a general shape, a rough outline. Move closer and the edges fray. Wisps trail off. Portions fade into clear air. At no point does the cloud announce where it stops being cloud. Large-scale cosmic structures behave in much the same way. Another useful comparison is a coastline. On a map it looks like a line. Zoom in and that line becomes jagged. Zoom further and it becomes fractal, endlessly complex. The length of the coastline depends on how finely it is measured. The coast is real, but its exact boundary depends on scale. The universe inherits this same ambiguity when structures become enormous. Because of this, astronomers often disagree on classification, not because observations are poor, but because definitions must be chosen. How dense does a region need to be to count as a structure? How far apart can galaxies be while still belonging together? Over what distance must alignment persist before it is meaningful rather than coincidental? Different research groups answer these questions in different ways, depending on what they're studying. Some focus on gravitational binding, others on shared motion, others on statistical excess above background density. Each approach highlights different aspects of reality. None capture the whole picture on their own. This is where computer simulations become essential. Modern cosmology relies heavily on simulations that model the growth of structure over billions of years. Starting from tiny differences in density shortly after the universe began, these simulations allow gravity, expansion, and matter to interact under known physical laws. The resulting patterns can then be compared to observations. What emerges from these simulations is strikingly familiar. Filaments form, voids open up, clusters appear at intersections. The cosmic web grows naturally from simple beginnings. Yet even in simulations, boundaries remain soft. Structures overlap. Density thresholds blur. The universe resists being chopped into clean pieces even in a computer. Simulations also reveal why extreme size is so hard to define. Large patterns arise not because there is a preferred maximum scale, but because matter responds to gravity across all distances available. Small structures form first. Larger ones emerge later as matter flows along filaments. The process is continuous. There is no obvious place to stop. This continuity explains why astronomers can look at the same data and reach slightly different conclusions about what counts as the biggest thing. One may see a single immense structure. Another may see several connected regions that should be treated separately. Both interpretations can be reasonable, depending on the criteria used. Reality, it turns out, is messier than diagrams suggest. Textbook illustrations often show clean filaments and well-defined voids, separated neatly for clarity. In the real universe, transitions are gradual. Filaments branch and reconnect. Voids contain substructure. Clusters sit within clusters of patterns. The universe is textured rather than tiled. There is a quiet lesson here about scale and expectation. The farther out one looks, the less useful sharp categories become. At small scales, precision matters. At large scales, trends matter more than boundaries. Statistics become the language of structure. This does not mean that the universe becomes vague or unknowable. It means that knowledge takes a different form. Instead of asking where something ends, astronomers ask how likely it is to find matter here versus there. Instead of naming edges, they measure contrasts. Instead of counting objects, they study distributions. Gentle humor finds its place in this shift as well. Humans ask for the biggest thing. The universe responds with a histogram, not an object, but a curve, not a border, but a gradient. It is a polite refusal to play by simple rules. As structures become statistical, the idea of ownership fades. A galaxy may belong partly to one filament and partly to another. A cluster may sit at the edge of a void without fully defining it. Membership becomes fuzzy. Belonging becomes conditional. This fuzziness is not accidental. It reflects how gravity works over long distances. Forces weaken gradually. Influences overlap. There is no cosmic zoning authority assigning parcels of space. Everything negotiates continuously with everything else. At this stage, the notion of the biggest thing begins to dissolve, not because nothing is large, but because largeness no longer attaches cleanly to singular entities. It spreads across relationships. It lives in patterns that cannot be circled neatly. What remains is not confusion, but a quieter understanding. The universe is not built like a collection of boxes. It is built like a field, dense here, sparse there, structured but softly. Once this perspective settles in, the need for sharp borders begins to relax. Size becomes something to describe rather than something to crown. The question shifts again, not toward a new candidate, but toward a deeper appreciation of how structure itself emerges. And in that appreciation, the universe feels less like a puzzle to be solved and more like a landscape to be slowly explored. At a certain point, widening the view no longer reveals larger structures made of matter. Instead, it reveals a limit to what can be known at all. Not a physical barrier, not a wall or an edge, but a boundary defined by information. This is where the idea of the observable universe enters the story. The word observable is doing careful work here. It does not mean everything that exists. It means everything from which light or any other signal has had time to reach us. Observation, in astronomy, depends entirely on messages travelling across space. Light carries those messages. So does radiation at other wavelengths. If a signal has not arrived, then whatever produced it remains beyond reach, at least for now. This immediately explains why the observable universe has a size. The universe has a history. It has not existed forever. There was a beginning, a moment when space itself was far hotter, denser, and smaller than it is now. From that moment onward, light began travelling outward in all directions. Some of it has reached Earth. Some of it is still on its way. Some of it will never arrive. The observable universe is the region from which information has had enough time to travel to us since that beginning. It is not defined by distance alone, but by time and motion working together. Space expands, light moves. The two interact in ways that are not always intuitive. One detail often surprises people. The observable universe is much larger than its age might suggest. Although the universe is roughly 13.8 billion years old, the observable universe has a radius of about 46 billion light-years. This is not because light travels faster than expected, but because space itself has been expanding while the light travels through it. A simple image helps here. Imagine dots drawn on a stretchable surface. As the surface expands, the dots move farther apart, even though none of them are moving across the surface themselves. Light behaves similarly. It travels through space, but space continues to stretch underneath it. By the time the light arrives, the source is much farther away than it was when the light began its journey. This expansion is gentle and uniform. There is no center, no preferred direction. Every region of space expands relative to every other. Galaxies are not flying through space away from us like debris from an explosion. Instead, the space between galaxies grows, carrying them along for the ride. Because of this, the observable universe is best thought of as a horizon. Not a physical boundary, but a limit of communication. Beyond that horizon, light has not had enough time to reach Earth. Those regions are not hidden behind anything. They are simply too far away in time as well as space. This distinction matters. The observable universe is not a container holding everything that exists. It is more like the portion of reality that has had time to say hello. Everything else remains silent, not because it is absent, but because its message has not arrived. There is no sharp edge to this horizon. It is not marked by a line or a wall. It is defined statistically by how far signals could have travelled under cosmic expansion. As time passes, the observable universe grows, slowly incorporating regions that were once beyond reach. Yet expansion complicates this growth. Some regions recede so quickly that their light will never arrive, no matter how long one waits. This introduces a quiet subtlety. The observable universe can grow while still leaving parts of the universe permanently unobservable. Not because observation fails, but because the geometry of space and time makes communication impossible. It is a reminder that limits do not always imply barriers. Sometimes they arise naturally from motion and scale. Importantly, this boundary is about information, not matter. Galaxies do not stop existing beyond the observable universe. Physics does not change abruptly. The laws governing matter and energy are believed to be the same everywhere. What changes is access. This is why astronomers are careful with language here. The observable universe is not the whole universe. It is the part that can, in principle, be studied. Everything beyond it remains speculative, not in the sense of being imaginary, but in the sense of being untestable with current or even future observations. There is a temptation to treat this boundary dramatically, to imagine standing at the edge of everything, to picture a final curtain beyond which nothing lies. but that instinct imports everyday thinking into a context where it does not belong. The observable universe does not end in a place. It ends in a condition. Beyond that condition, there may be more galaxies, more structures, more patterns similar to those already seen. There may be regions, much like the local universe, repeating endlessly. Or there may be variations, different densities, different histories current evidence cannot decide. And that uncertainty is not threatening. It is calm. The universe does not demand to be fully known in order to function. It does not require human awareness to continue unfolding. The observable universe provides a complete enough stage for understanding the laws that govern what can be seen. Those laws can then be extended cautiously beyond observation. In this sense, the observable universe becomes the largest meaningful boundary humans can discuss scientifically. Not because nothing lies beyond it, but because meaning in science depends on evidence. Where evidence cannot reach, claims must soften. There is something reassuring in this restraint. Rather than filling the unknown with speculation, science leaves space open. It acknowledges what can be said and what cannot. It allows the universe to be larger than comprehension, without turning that fact into a problem. Gentle humour fits here too. Ask for the biggest thing, and the universe eventually answers with a horizon, not an object, not a structure, but a limit on conversation. It is as if reality says, this is as far as the discussion can go for now. Within that horizon, everything that has been described so far exists. Galaxies, clusters, filaments, voids, patterns layered on patterns. The observable universe contains all of them, not as a container, but as a shared history of light and time. Beyond it, there is no reason to assume emptiness, only silence. And silence, in this context, is not absence. It is simply distance that has not yet been crossed, or perhaps distance that never will be. Either way, it invites a quieter response than awe or anxiety. It invites patience. The observable universe is not the biggest thing because it dominates everything else. It is the biggest thing because it defines the reach of understanding. It marks the boundary between what can be known directly and what must remain inferred. That boundary does not close the story, it keeps it open. In accepting it, the question of the biggest thing shifts once again, away from trying to outgrow the universe and toward understanding how far knowledge itself can extend. At this point, the most obvious answer finally asks to be addressed directly. If everything discussed so far exists within the universe, then why not simply say that the universe itself is the biggest thing? It feels clean, comprehensive, difficult to argue with. And yet, the moment this answer is examined closely, it begins to behave like all the others. It softens at the edges. The first complication is surprisingly basic. Is the universe even a thing? In everyday language, a thing is something that sits within a larger context. A mountain exists on a planet. A planet exists in a system. A system exists in a galaxy. Each thing is defined partly by what surrounds it. The universe, by definition, has no external container. It does not sit anywhere. It includes space itself. Calling it a thing stretches the word beyond its usual meaning. In physics and cosmology, the universe is better described as a totality. All space, all time, all matter and energy, all physical processes. This makes it difficult to compare the universe to anything else, because there is nothing outside it to serve as reference. Comparison requires contrast. The universe offers none. Still, size can be discussed in another way, not by asking what the universe is inside, but by asking how much of it exists. Is it finite or infinite? Does it have a total volume, or does it extend without limit? These questions sound abstract, but they arise naturally from observation and theory. Modern cosmology suggests that space is expanding uniformly. Galaxies move farther apart over time, not because they are travelling through space, but because space itself is stretching. Measurements of this expansion, combined with observations of the cosmic background radiation, allow scientists to model the overall geometry of the universe. Some of these models describe a universe that is finite but unbounded. Much like the surface of a sphere, which has a finite area but no edge, space could curve back on itself, travel far enough in one direction, and eventually you might return to where you started without ever encountering a boundary. In such a universe, size exists, but edges do not. Other models allow for an infinite universe. In this case, space extends endlessly in all directions. There is no total volume, no final scale, no biggest extent. Every region resembles every other on sufficiently large scales, and the observable universe becomes just one small patch within something vastly larger. Both possibilities are consistent with current observations. The universe appears very close to geometrically flat, which means that if it is finite, it is extremely large compared to what can be observed. If it is infinite, then the observable universe is an even smaller sample of a much grander whole. Present data cannot distinguish definitively between these options. This is where the idea of infinity enters the conversation. Infinity often feels like a place, somewhere far away, a direction you could point toward if only you travelled long enough. In mathematics, infinity is not a location. It is a concept, a way of describing something without limit. When cosmologists talk about an infinite universe, they do not mean a destination that could be reached. They mean that for any chosen distance, more space exists beyond it. There is no largest number that measures the universe's size, no final boundary to approach. Infinity describes a property of extent, not a region. This distinction matters because it changes how the question feels. If the universe is infinite, then asking whether it is the biggest thing becomes meaningless. There is nothing larger, but not because it dominates everything else. Because size itself no longer has an upper bound. If the universe is finite, the question becomes slightly more grounded but no less subtle. A finite universe could have a total size yet still lack edges. It could be complete without being contained. In that case, the universe would indeed be the largest possible physical structure, but not in a way that fits neatly with everyday notions of bigness. In both cases, humility becomes essential. Cosmology deals with scales so vast that intuition falters. Observations are limited, models are tested indirectly, conclusions are held lightly, ready to be revised as new evidence arrives. This is not uncertainty born of ignorance. It is caution born of respect for the limits of measurement. Scientists are careful not to claim final answers here. The history of cosmology offers many examples of confident statements, later softened or overturned. Each generation pushes understanding outward, only to discover new layers of complexity waiting beyond. There is something quietly appropriate about this. The universe, which contains everything, does not yield easily to summary. It resists being reduced to a single label. Even calling it the biggest thing feels slightly off, as if the language itself is too small. Gentle humour can live here as well. Ask whether the universe is the biggest thing, and science replies by asking what is meant by thing, by biggest, and by universe. The question multiplies rather than resolves, not out of stubbornness, but because clarity demands precision. Rather than closing the conversation, this moment invites a shift in perspective. Perhaps the question is not about identifying a final champion of size. Perhaps it is about understanding why such champions are difficult to name at all, why the universe keeps encouraging broader frames rather than singular answers. Seen this way, the universe being the biggest thing is both true and incomplete. It is true in the sense that nothing physical exists outside it. It is incomplete because size, as a comparative idea, loses meaning when there is nothing left to compare. Sitting with this openness does not require discomfort. It can be restful. The universe does not rush to define itself. It allows room for uncertainty, for multiple models, for quiet refinement over time. Knowledge grows not by claiming completion, but by remaining flexible. As the question loosens its grip, something else becomes clearer. The search for the biggest thing has never really been about size alone. It has been about orientation, about finding where understanding naturally comes to rest. And perhaps that resting place is not a final answer, but a reframing a recognition that the universe is not a thing to be measured against others, but the context in which all measurement occurs. With that recognition, the question begins to change shape once again. The question of the biggest thing has a habit of changing, not because it is poorly asked, but because understanding itself is never still. Science does not advance by locking answers in place. It advances by revisiting them, gently adjusting their shape as new ways of seeing become available. One of the simplest reasons answers evolve is that instruments improve. Every major shift in astronomical understanding has followed a change in how the universe is observed. Early telescopes revealed moons around planets and resolved stars as distant suns rather than points of light. Later instruments extended vision beyond visible light, uncovering structures made of hot gas, cold dust, and invisible mass. Each new window widened the frame. When telescopes grew more sensitive, galaxies multiplied. What once appeared as faint smudges became vast systems filled with structure. When surveys expanded, clusters appeared. When depth was added, filaments and voids emerged. The universe did not change. The view did. With each improvement, questions that once felt settled were reopened. What counts as a galaxy? Where does a system end? How large is a structure when its faint edges finally come into view? Answers shifted not because earlier scientists were careless, but because they were working with less information. Definitions evolve alongside instruments. Scientific terms are tools, not monuments. They're shaped to fit the problems being studied. When new phenomena are discovered, old definitions may stretch or be replaced. This is not backtracking, it is refinement. Consider how the idea of a galaxy itself has changed. There was a time when spiral galaxies were thought to be clouds within the Milky Way. Only when distances could be measured reliably did it become clear that they were entire systems far beyond it. The definition of galaxy expanded, and with it, the scale of the universe. The same pattern appears repeatedly. Structures once thought to be isolated are revealed to be connected. Objects once thought to be simple are found to have complex components. Boundaries once drawn sharply are softened as new data fills in the gaps. Historical examples show this clearly. The known size of the universe expanded dramatically in the early 20th century as distances to other galaxies were established. Later, the discovery of cosmic expansion reshaped ideas about space and time themselves. More recently, the recognition of dark matter and dark energy altered how mass and structure are understood on the larger scales. None of these shifts invalidated what came before. Each one placed earlier knowledge into a broader context. Earlier models were not wrong, they were incomplete. This gradual expansion of understanding is sometimes mistaken for uncertainty in the everyday sense. It can sound as though science is unsure of itself. In reality, it reflects a disciplined humility. Claims are limited to what evidence supports. When evidence grows, claims are adjusted. There is strength in this flexibility. A system that refuses to change in the face of new information quickly becomes brittle. Science remains resilient precisely because it allows its answers to move. The question of the biggest thing changes for the same reason maps change as they become more detailed. Early maps capture coastlines roughly. Later ones add bays, inlets, and subtle curves. The land was always there. The representation improves. Uncertainty in this context is not a flaw to be eliminated. It is a signal that the question sits near the edge of what can be known. At those edges, careful language matters. Overconfidence closes doors. Curiosity keeps them open. For the listener, this can be reassuring. It means that not knowing everything is not a failure. It is the normal state of inquiry. The universe does not demand complete understanding in order to be studied meaningfully. Partial views can still be accurate within their limits. Gentle humor finds a home here as well. Ask a scientist for a final answer, and you may receive a provisional one instead. Not because the scientist is evasive, but because experience has taught caution. Nature enjoys surprises. Maintaining calm continuity through changing answers requires patience. It means accepting that knowledge is layered, that today's explanation may be nested inside tomorrow's, that progress often looks like complication before it looks like clarity. The biggest thing question has survived precisely because it adapts. It absorbs new discoveries without breaking. It remains useful not as a riddle with a single solution, but as a guide for exploring scale, structure, and limitation. As instruments improve and theories mature, the question will continue to shift. New candidates will appear. Old ones will be reinterpreted. Boundaries will be redrawn. None of this diminishes what is already known. Instead, it reveals something quietly important. Science is not a collection of final answers. It is a process of listening carefully to the universe and adjusting descriptions accordingly. In that sense, the changing nature of the question is not a problem to solve. It is evidence that understanding is alive, responsive, and still unfolding. And with that recognition, the search for the biggest thing becomes less about reaching an endpoint and more about staying oriented as the view continues to widen. By this point, scale has grown very large indeed. Galaxies have blurred into patterns. Patterns have softened into horizons. The universe itself has entered the conversation, and somewhere along the way, it becomes easy to feel that size carries weight beyond measurement. That bigger somehow means more important. This feeling is understandable. In everyday life, size often comes with consequences. Larger animals tend to dominate ecosystems. Bigger machines exert more force. Larger organizations influence more people. It is natural to carry that intuition outward, to assume that the largest things in the universe must also be the most meaningful. The universe does not seem to agree. In nature, size and significance are only loosely connected. Small systems can be extraordinarily complex. Large systems can be surprisingly simple. Importance depends on context, not scale. A single cell, for example, contains intricate machinery operating with remarkable precision. Chemical processes unfold in carefully regulated sequences. Information is stored, copied, and translated. Feedback loops maintain balance. All of this happens on a scale far too small to see with the naked eye, yet it is essential for life. Meanwhile, a vast region of empty space may stretch across millions of light years and do very little at all. The same principle applies throughout the cosmos. A modest star system can host planets with stable climates, complex chemistry, and long histories. A massive galaxy cluster, by contrast, may be dominated by hot gas and dark matter, evolving slowly and quietly over billions of years. One is not more important than the other. They simply play different roles. Astronomy reinforces this lesson repeatedly. Some of the most influential processes in the universe occur on small scales. Nuclear fusion happens in the cores of stars, not across entire galaxies. Planet formation unfolds within thin disks of dust and gas, not across clusters. Even the chemical elements that make up planets and living things are forged in specific stellar environments, not spread evenly through space. Large structures provide context. Smaller ones provide detail. It can help to think in terms of balance rather than hierarchy. The universe is not organized like a ladder, with importance increasing step by step as size grows. It is organized more like a landscape, with features of different scales contributing in different ways. Mountains matter, rivers matter, valleys matter. None replace the others. Everyday analogies can make this feel more familiar. A city depends on vast infrastructure, power grids, water systems, transport networks. But it also depends on small components, individual buildings, local streets, quiet routines. Remove any one layer and the whole system suffers. Size alone doesn't determine value. The same is true in physics. Fundamental particles are tiny, yet they determine the behavior of all matter. Physical laws operate uniformly, whether applied to a grain of dust or a galaxy cluster. The equations do not grow more important as the systems grow larger. They simply play out across broader canvases. This perspective gently removes emotional weight from comparisons of scale. Discovering that something larger exists does not diminish what is smaller. A planet does not become less interesting because a galaxy exists. A galaxy does not lose meaning because the universe may be far larger still. Even within astronomy, the most studied objects are often not the biggest ones. Stars similar to the Sun receive close attention because they are stable and long-lived. Planets of modest size are examined carefully because they're easier to characterize and more likely to host complex processes. Small does not mean trivial. Often, it means accessible. There's also stability to consider. Larger systems tend to change slowly. Their vastness smooths out variation. Smaller systems can respond more quickly, adapt more readily, and develop intricate structures. A small system can be dynamic in ways a large one cannot. This balance appears again and again. Large-scale structure provides the framework. Small-scale structure provides the activity. Neither dominates. Both are necessary. When scale is stripped of significance, something calming happens. The need to compare fades. The impulse to rank relaxes. The universe no longer feels like a competition of sizes, but a collection of interlocking processes, each appropriate to its scale. This shift is especially helpful as the topic moves toward emotional settling. Vastness can feel overwhelming when interpreted as hierarchy. When interpreted as diversity, it becomes gentler. There is room for everything. Gentle humor fits here too. The universe contains structures so large they defy intuition, yet it still runs on the same basic rules everywhere. No special treatment for the biggest things. No shortcuts. Gravity pulls. Energy flows, time passes, size changes, none of that. From this view, the question of the biggest thing becomes less pressing, not because the answer is known, but because its emotional charge is softened. Knowing that something larger exists does not threaten understanding, it simply expands context. Balance replaces comparison, coexistence replaces ranking. As pacing slows, it becomes easier to sit with this idea. The universe is not built to impress or intimidate. It is built to function. Scale is a consequence of that functioning, not a measure of worth. Smaller systems remain rich with detail. Larger systems remain impressive in scope. Each reveals different aspects of the same underlying reality. Neither needs to overshadow the other. With that perspective in place, the search for the biggest thing begins to quiet. The question does not disappear, but it loses urgency. It becomes something to explore thoughtfully rather than something to resolve. And in that quieter space, attention can begin to drift away from competition altogether toward a more settled appreciation of how all scales fit together. The universe does not ask to be ranked, it simply unfolds. It is easy to forget when thinking about enormous distances and structures that life unfolds quietly within them. Galaxies stretch across hundreds of thousands of light years. Clusters span millions. The observable universe reaches far beyond imagination. And yet, here on Earth, mornings still arrive on time, seasons still change predictably. The night sky turns overhead with gentle regularity. Humans live inside enormity without ever needing to confront it directly. This is not because cosmic scale is hidden, but because it is stable. The vast systems that shape the universe evolve slowly, on timescales so long that they appear fixed from a human point of view. The rotation of Earth, the orbit around the Sun, the steady rhythm of day and night, these motions are embedded within much larger motions that change almost imperceptibly. The solar system moves through the galaxy. The galaxy drifts within a larger structure. That structure follows the expansion of space itself. All of this is happening continuously, yet none of it disrupts daily life. The forces involved are balanced. Motion is smooth. Change unfolds gradually. This stability is not accidental. It is the result of physical laws operating consistently across enormous spans of time. Gravity shapes orbits that repeat with remarkable precision. Energy flows settle into steady patterns. Systems that persist do so because they are balanced enough to endure. On human timescales, the universe is calm. Even events that sound dramatic when described in isolation occur so far away, or over such long durations that they barely register locally. Stars are born and die elsewhere in the galaxy, but the night sky looks much the same year after year. Galaxies merge over billions of years, but the stars within them continue their slow paths without sudden upheaval. Cosmic size does not translate into constant disruption. In fact, it often means the opposite. Larger systems tend to change more slowly than smaller ones. Their sheer scale smooths out fluctuations. Local disturbances are absorbed without consequence. Stability increases with size. This is why it is possible to live comfortably inside such a vast universe. The larger structures provide context, not interference. They set the background conditions under which smaller systems operate, then remain largely hands-off. Cycles play an important role here. Earth's orbit traces the same path year after year. The Moon's phases repeat predictably. The Sun rises and sets with reassuring consistency. These cycles are nested within larger ones, which are themselves nested within larger still. Each layer turns quietly within the next. Seen this way, enormity becomes a container rather than a threat. The universe is vast enough to allow countless systems to run independently, without crowding or conflict. There is room for regularity. Long timescales also soften perspective. The Milky Way completes a slow rotation over hundreds of millions of years. Galaxy clusters evolve over billions. The expansion of the universe unfolds across spans so long that they resist emotional interpretation. Against this backdrop, a human lifetime is brief, but not insignificant. It fits comfortably within the rhythms already in place. There is reassurance in knowing that nothing urgent is demanded by the universe's size. It does not require constant adjustment. It does not accelerate unexpectedly. It does not threaten to overwhelm through scale alone. Vastness in this context is passive. Even the laws governing the universe contribute to this sense of calm. Physical constants remain stable. Processes follow repeatable patterns. The same rules apply everywhere, whether in a distant cluster or a quiet laboratory on Earth. This uniformity allows prediction. Prediction allows trust. From the perspective of everyday life, cosmic size becomes almost irrelevant. The distances to distant galaxies do not affect the weather. The size of the observable universe does not alter the length of a day. The expansion of space does not pull objects apart locally. Gravity holds nearby systems together firmly enough that larger scale changes remain background noise. Gentle humor fits naturally here. Humans sometimes imagine that learning about cosmic vastness should feel unsettling. In practice, it mostly confirms how well things are already working. The universe has been large for a very long time, and life has managed just fine. This is not to say that change never occurs. On geological timescales, continents shift. On astronomical timescales, stars evolve. But these changes are slow, giving systems time to adjust. Sudden disruption is rare. Continuity is the norm. Living inside enormity means inhabiting a small, stable pocket within a much larger, slowly changing whole. It means that daily concerns unfold against a backdrop that is vast but steady. The universe does not loom, it holds. As the pacing eases, attention naturally begins to drift away from the question of size and toward the feeling of placement. Not smallness, but situatedness. Being somewhere specific within something expansive, there is comfort in this idea. Enormity does not diminish the local, it supports it. It provides room for repetition, for habit, for long-term patterns to establish themselves. The night sky may hint at scale, but it does not intrude. The universe's size becomes something like a deep ocean beneath a calm surface, immense, ancient, and quietly present, while the surface continues its gentle motions. Knowing the depth exists does not disturb the waves. As emotional closure approaches, this perspective helps settle the mind. The universe is not rushing, it is not leaning in, it is not demanding response. It is spacious enough to allow life to proceed at its own pace. Humans function within vast systems not by confronting them, but by relying on their stability, by trusting that the rules remain consistent, by living within cycles that have been repeating long before any single observer noticed them. Enormity, when viewed this way, becomes less about scale and more about reliability, less about awe and more about assurance. The universe is large, yes, but it is also patient, and in that patience there is room to rest. After travelling through stars, systems, galaxies, clusters, patterns and horizons, there comes a natural pause. Not because everything has been resolved, but because the urge to resolve begins to soften. The question that started the journey does not disappear, but it loosens its grip. What is the biggest thing no longer feels like something that must be answered cleanly. This is an important moment. Many questions in science are not designed to close neatly. They are designed to orient understanding, to provide a direction rather than a destination. The question of size, especially at cosmic scales, belongs firmly in this category. It opens perspectives, it invites comparison, it stretches intuition, but it does not require a final verdict. Science is comfortable with this kind of openness. In many areas, it prefers ranges to endpoints, confidence intervals rather than single values, models rather than declarations. This is not hesitation, it is precision expressed honestly. When astronomers measure distances, they often give uncertainties alongside the numbers. When they describe structures, they speak in terms of likelihood and probability. When they model the universe, they explore families of possibilities rather than one fixed outcome. Reality is complex enough to deserve that care. The biggest thing question benefits from the same treatment. Depending on how size is defined, the answer shifts. Sometimes the observable universe feels like the largest meaningful boundary. Sometimes large-scale structure takes that role. Sometimes the universe as a whole enters the frame, though even that resists easy categorization. None of these answers cancel the others, they layer. Layered answers are not incomplete answers, they are answers that respect context. Comfort grows when this is accepted. The need to rank and finalize gives way to curiosity that is calmer and more patient. Instead of asking which answer wins, attention turns to why different answers exist at all, what each one reveals, what each one leaves open. This approach mirrors how science itself progresses. Questions are revisited rather than retired. Concepts are refined rather than replaced outright. Understanding deepens through accumulation, not through sudden closure. There is something quietly reassuring about this process. It suggests that knowledge does not require urgency. It unfolds over time, at a pace set by evidence rather than expectation. The universe does not mind being understood gradually. Gentle humour fits naturally here. Humans often ask questions as if the universe is waiting to hand over a final answer, neatly wrapped. In practice, it offers a collection of perspectives instead. Not an ending, but an invitation to look again from a slightly different angle. Letting the universe be big means letting go of the need to contain it in a single idea. It means accepting that scale can be described without being conquered. That understanding can be accurate without being complete. This does not diminish the value of knowledge, it enhances it. Knowing where explanations soften is part of knowing where they are strongest. Boundaries of understanding are not failures, they are landmarks. The language of ranges illustrates this well. When cosmologists talk about the size of the observable universe, they give approximate values, grounded in measurement and theory, yet open to refinement. When they discuss what lies beyond observation, they speak carefully, outlining possibilities without insisting on certainty. This restraint is not caution born of fear. It is confidence born of method. Layered answers also leave room for future insight. New instruments may extend observation, new data may sharpen models, concepts that feel settled today may be reframed tomorrow. By not insisting on finality, science keeps space open for growth. For the listener, this openness can feel restful. There is no pressure to memorize a single correct response, no need to hold on to a definitive conclusion. The question can remain alive, gently evolving as understanding does. Calm curiosity replaces urgency. Wonder remains, but it is quieter, more spacious, less demanding. At this stage, it becomes clear that the question was never only about size, it was about perspective, about how humans relate to scales far beyond everyday experience, about learning to think comfortably in layers rather than absolutes. Letting the universe be big also means allowing it to be unbothered by human categorization. It does not adjust itself to fit questions. It reveals itself gradually, according to laws that operate independently of how satisfying the answers feel. There is a subtle freedom in this. The universe does not require endorsement or completion. It does not need to be reduced to a final diagram. It continues, patient and expansive, whether fully understood or not. As this perspective settles in, the question of the biggest thing transforms. It becomes less about identifying an object or boundary, and more about recognizing a relationship. The relationship between observation and reality, between measurement and meaning, between curiosity and acceptance. This transformation does not close the journey. It prepares it to end gently. Rather than concluding with a declaration, the mind can rest with a sense of orientation, knowing how the universe is structured, knowing where definitions hold and where they blur, knowing that uncertainty is not an obstacle, but a natural feature of exploration. In this light, the biggest thing is not something to be captured. It is something to be approached with patience, something to be described from multiple angles, each adding texture rather than resolution. The universe is large enough to accommodate this approach. It does not demand haste. It does not reward oversimplification. It offers scale as context, not as a challenge. Letting it be big is an act of trust. Trust that understanding does not require closure. Trust that curiosity can remain open, ended without losing value. Trust that knowledge grows best when allowed to breathe. As the final reflective landing draws nearer, this trust becomes the lasting takeaway. Not an answer, but a posture, a way of holding questions gently without needing to press them flat. The universe remains big, bigger than any single description, bigger than any diagram, bigger than any answer that could be spoken aloud. And that is not a problem to solve, it is simply how things are. The question that began this journey sounded simple at first. What is the biggest thing in the universe? It felt like something that could be answered by pointing outward, by identifying a vast object or a distant boundary and letting the scale speak for itself. Yet along the way, the question quietly changed. It widened. It softened. It learned to ask something slightly different. Instead of demanding a single answer, it began to explore how answers depend on perspective, how size can mean width, mass, influence, duration, or reach, how some of the largest features in existence are not objects at all but patterns, how boundaries often reflect limits of observation rather than limits of reality. By the end, the question no longer asks for a champion of scale, it asks what scale itself can teach. One of the clearest lessons is that perspective matters more than absolute size. From one viewpoint, a star can feel enormous. From another, it becomes one point among billions. A galaxy can seem vast until it dissolves into a filament. A filament can feel immense until it blends into the observable universe. Each scale is real. None cancels the others. Understanding emerges not from choosing the correct scale, but from learning to move between them comfortably. This movement reveals something quietly reassuring. Partial understanding is still understanding. Knowing how something fits locally, even if its full extent remains unknown, is enough to make sense of experience. The universe does not require total comprehension in order to be meaningful. In fact, much of science operates exactly this way. Models describe limited domains. Theories apply within defined ranges. Knowledge grows by layering insights, not by eliminating uncertainty entirely. What matters is not having the biggest answer, but having an answer that works where it is used. This is especially true when dealing with something as vast as the universe itself. No single description can capture it fully. Every explanation highlights certain features and leaves others in the background. This is not a flaw. It is an honest reflection of scale. There is also a gentler lesson here about emotional response. Vastness is often presented as something overwhelming, something meant to provoke awe or insignificance. Yet the universe does not insist on that reaction. When approached slowly, scale becomes contextual rather than confrontational. Large structures unfold over immense timescales. Change is gradual, patterns persist. The universe feels less like a dramatic spectacle and more like a steady environment. Big does not mean urgent. It does not mean unstable. Often it means the opposite. This steadiness allows life to proceed quietly within it. Orbits remain reliable. Physical laws remain consistent. The same principles apply everywhere, from the smallest interactions to the largest arrangements. Scale does not disrupt continuity. It supports it. Even the limits of knowledge fit into this calm picture. The observable universe marks a boundary, not because reality ends there, but because information does. Beyond that horizon, the universe may continue, or it may not. Current evidence cannot decide, and that uncertainty does not weaken what is known within the horizon. Science is comfortable with this. It does not rush to fill silence with speculation. It acknowledges where understanding rests and where it must pause. This restraint is part of its strength. There is something quietly grounding about recognizing that not every question needs closure. Some questions are meant to remain open, not as unresolved problems, but as spaces for continued orientation. The biggest thing question turns out to be one of these. It invites curiosity without demanding finality. It encourages exploration without pressure. It teaches how to think, not what to conclude. Gentle humor can be found in how this unfolds. A question that seems to ask for a single enormous answer ends up offering many smaller insights instead. The universe responds not with a trophy, but with perspective. In that sense, the biggest thing is not an object or a structure. It is the framework within which understanding grows, the ability to hold multiple scales at once, to accept that some boundaries are defined by observation, to recognize that knowledge can be precise without being complete. This perspective leaves the listener grounded rather than awed, situated rather than diminished. The universe does not loom, it surrounds, steadily and without urgency. As this journey comes to rest, there is no need to summarize aggressively, or to compress everything into a final statement. The ideas have already settled into place. Stars remain stars, galaxies remain galaxies, patterns remain patterns. The observable universe remains a horizon of information. Beyond it, the universe remains itself, whether known or unknown. Continuity is the lasting impression. The universe is not rushing toward an endpoint. It is not waiting for a final description. It unfolds according to its own rhythms, patient and unhurried. Understanding follows at a slower pace, and that is enough. In the end, the biggest thing teaches something simple and steady. That scale is contextual. That meaning does not depend on magnitude. That clarity can coexist with uncertainty. And perhaps most importantly, that it is possible to live comfortably inside a universe that is larger than any single answer, without needing to shrink it down to feel at home. The universe remains vast, understanding remains partial, and life continues quietly within both. Nothing more is required. The question that opened this journey never truly asked for a measurement. It asked for orientation, for a way to place understanding somewhere steady while everything else expanded outward. What began as a search for the biggest thing slowly became something else. A lesson in scale, a lesson in limits, a lesson in how the universe prefers patterns over prizes, ranges over endpoints, and patience over finality. Along the way, size stopped behaving like a competition. Bigger did not replace smaller. Larger did not erase nearer. Each scale revealed something different, and none of them claimed authority over the rest. Stars mattered where stars mattered. Galaxies mattered where galaxies mattered. Patterns mattered where individual objects dissolved into structure. The universe did not offer a single answer because it did not need to. It offered context instead. This is one of the quieter strengths of scientific understanding. It does not insist that every question resolve into a sentence that can be underlined and closed. It allows some questions to remain open, not as gaps in knowledge, but as spaces where perspective can settle. The observable universe marks a boundary of information, not of existence. Beyond it, reality may continue in familiar ways, or in ways that differ subtly or profoundly. The evidence does not yet decide, and the undecided space does not diminish what is already known. It simply reminds that understanding grows outward, not all at once. What matters most is that everything needed for clarity already exists within reach. The laws that govern distant galaxies are the same laws shaping the quiet motion of Earth. The forces that arrange the cosmic web also keep familiar systems stable and predictable. Scale does not interrupt continuity, it preserves it. The universe is vast, but it is not urgent. It does not rush explanations. It does not demand conclusions. It unfolds steadily, allowing understanding to follow at a human pace. That may be the most grounding lesson of all. The biggest thing is not something that needs to be named, circled, or finalized. It is the recognition that reality is layered, that knowledge is contextual, and that partial understanding is not a failure. It is the normal, healthy state of curiosity. Nothing here asks to be resolved tonight. Nothing needs to be settled before rest arrives. The universe will remain large tomorrow, and the next day, and long after any single question has faded. Understanding will continue, slowly, carefully, one layer at a time. For now, it is enough to know that scale does not diminish meaning, that uncertainty does not erase clarity, that vastness can be calm. The universe is big,